As we come to the end of this course, it's time to reflect a little and think about what are the real-world applications for these operating system concepts. Why is it so important to know about how operating systems are constructed and what kind of operating principles and high-level goals they have? In particular, we're going to look at a couple of real-world examples, that is different types of virtualization, and also a concept called two-tier compilation. Both of these virtualization products, such as virtual machines and containers, are something that an IT professional will run into very often. Two-tier compilation, on the other hand, is something that you probably have already run into. It's just something that has not been explicitly explained because it's a concept that is in the background. And you have to know a little bit about how operating systems work in general, how high-level code is translated into something that is machine executable, and without that knowledge, you would be none the wiser. But in practice, these both are something that you run into very often in the real world. So the full name of this course module is actually Operating Systems and Server Environments. Now, the last assignment on this course is actually about implementing a server, but we should still talk a little bit about servers and how they fit into the picture of these operating system concepts that we have been talking about. So first of all, in practice, many of these operating system concepts on this course are extremely important in the server context. That is because, well, let's think back, what is the operating principle of a server? So in practice, a server is just a computer or a computer service that is always available. So it's basically a computer system that hosts some resources for other computers or other computer programs. And these other computer programs do not have to have this resource because they can just ask the server for it. There are multiple examples of servers in practice. In particular, probably the most common one is a web server, but there are also some system services in an operating system that are called servers. If you pull the Windows Task Manager up, for instance, you might see something like this. So a server is not only a dedicated computer in a data center, it is much, much more. So by a server, what we actually mean is some service hosted somewhere, either inside an operating system or on a dedicated computer or in a cloud somewhere where there is a set of resources that are always available. Then how does a server actually work? So as said, the server is a computing resource somewhere, which basically waits until there is some requester, which we call a client, that needs some resource that is hosted on that server. So what a server does, it actively waits for some client to request a resource from it. Then the next step would be to authenticate that this resource is something that, or this requester is someone who we are supposed to serve these requests, but that's not really a topic of discussion for today. Then the server is responsible for fulfilling that request, i.e. Fetching the resource that was requested and returning the resource to the client that requested it in the first place. And then finally, we jump back to waiting for the client requests. So what a server does in reality is to repeat these 5 steps, wait for client requests, serve those requests, and then jump back to waiting again. Now, if we consider how a server can actually do that, so how does a server supply resources for other computers, other programs? So a server probably wants to keep all of these requests isolated from each other, because one request may not or should not interfere with others. And better yet, this one request or one client should not get any data from other requests. And all of these requests should be served with equal efficiency. If you think about this starts to sound a lot like the tasks or objectives that exist for an operating system. So in practice, a server does many of the same things that an operating system does. And of course, because a server is a computer also running an operating system, it turns out that a server can do a lot of this by using the concepts, the tools, the mechanisms provided by the operating system. So in order to do what the server needs to do, it can actually delegate some of this responsibility to its host operating system. One of the ways that a server can do all of that, well, it can use the operating system provided virtualization tools. So if you remember, the objective of the virtualization abstraction is to give some program its own virtual processor and memory. And it does this using the process abstraction. Now, what this process abstraction looks like in practice, well, on the Windows operating system, that abstraction is called a thread. And in Linux, it's also called a thread or a process. But the way we access this abstraction is through a system call called fork. And now, depending a little bit of whether you're programming in the Windows or in the Linux environment, things look a little different, but the concept behind them is similar. So both threads and this fork system call are used for creating new child processes, new child threads for execution. So in the Windows lingo, it says a thread for execution, and in the Linux terminology, it's creating a child process. Of course, we are used to talking about virtualization in a completely other context, which is virtual machines. So tools such as VMware or VirtualBox or Hyper-V, which are software packages, applications that provide these virtual platforms for other programs and operating systems, so that you can run an operating system within an operating system. This, of course, is what we mean by virtualization in our everyday talk, so that's virtual machine. Another contemporary virtualization technique is something called a container, which is another take on virtual machines. And this you will also probably run into if you do any sort of IT work related to servers or services or cloud services particularly. So the idea behind a container is that instead of a full-blown virtual machine inside an operating system, we can have a container which only contains some necessary code and libraries to run an application. So a very lightweight virtual machine. And all of the other resources needed, such as hardware and input-output, well, that is something that the containers share with their host operating system. Besides virtualization platforms like the virtual machines just discussed, there is another phased virtualization that is less talked about. And that is the concept called two-tier compilation. Now, what two-tier compilation basically means, it's a way of compiling code to that is ultimately ultimately ends in machine executables in a slightly different way to what we have been describing so far. So in the beginning of the course, we looked at something like this. So basically, the idea that we have some high-level code on the left, the high-level code goes into a compiler, and the compiler then compiles it into a set of binary instructions which are machine executable. Well, it turns out that this is often actually not the way how code is compiled. What actually happens is that we have at first some high-level code. It could be in different programming languages, say C# or Visual Basic, or even something called J#. This code then goes through a compiling stage. And as the result of this compilation, there is not machine binary, but instead, in this example, something called an intermediate language, or in specific Microsoft.NET language, it's common language runtime or common intermediate language. And that common intermediate language then, which is still platform in specific, can be translated into platform specific binaries. So there are in fact two steps or two compilation steps in this process. So what we actually do when we want to execute high-level code is that in order for this to work, we need to translate high-level code into some intermediate language, and then we need to translate that intermediate language to machine code. And these often are actually two different steps rather than just one big step as we have depicted before. So the idea of two-tier compilation, these two steps instead of one, is actually pretty old. It was used in the implementations of programming languages already in the 1970s. And it made a comeback in the 1990s because of programming languages or programming language families such as Java or Microsoft.NET, because they used this particular approach to code compilation. So why would some compilation process do compiling twice instead of just once? Isn't that adding complexity? Well, funnily enough, it actually reduces complexity for the following reason. So let's imagine we have what is called a direct compilation right here in the left or on the left. So if we need to do a translation between some high-level language and some hardware platform, that requires one translation or one compiler. So we need one compiler that understands this input language and also the hardware specification on the specific platform. And basically, we need to have as many compilers as we have both languages and hardware platforms. So if we have N supported languages and we have M supported hardware platforms in our computer system, we would need N times N M compilers in this process to translate all of these high-level languages to these different hardware platforms. And you might think, so how is this relevant? Well, it turns out there are a lot of different computer architectures and a lot of different programming languages. There must exist at least 100,000 different programming languages, and there are probably thousands of different processor architectures. So this creates a lot of complexity. So for all of these language hardware platform pairs, you would need a different compiler. So the idea behind two-tier compilation on the right is that instead of having a direct compilation between languages and hardware platforms, we compile individual high-level languages into some intermediate language, which is then compiled again into some specific version of hardware or machine code. And this greatly reduces the number of compilers that we would need. So for N languages and M platforms, we would require exactly N plus M translations or compilers. So we came down from N times M to N plus M. So the idea behind two-tier compilation is rather simple. Instead of running translated binary code on a real hardware, we create some intermediate language and interpret it using a virtual machine that runs on the real hardware. And this virtual machine is an abstract model of a computer which has no real implementation. It's implemented only in software. And the virtual machine can be an implementer for some physical real computer architectures as well. This really does not matter, but the point is that we are only running this high-level code on some virtual machine instead of translating a machine binary for some real computer architecture. Virtualization makes sense for a number of reasons. So first of all, it's easy to make programs portable for different computer architectures. And making the virtual machine for different hardware platforms is not really a complex task either. So programs running on top of the virtual machine can be written in a way that they are independent of the hardware properties. And that is, of course, a good thing because we are decoupling hardware from high-level code. There are different approaches to constructing virtual machines for this purpose. The virtual machine can be implemented purely in software. It can be built for an embedded system practically on the hardware level, or we could also translate virtual machines machine code or intermediate code directly to the hardware's machine language. So this approach gives us a little bit of versatility on how to end up with something that's a machine executable on the particular computer hardware. Finally, what are the key takeaways from this lecture? So we basically talked about virtualization. So let's give virtualization, or these different types of virtualization, some nice high-level names. So first of all, we talked about virtualization as an abstraction. So we talked about the process abstraction. And in particular, we talked about how servers use the process abstraction to do their job. Then we also looked at virtualization as a platform, so virtual machines and also containers. Finally, we talked about virtualization as a framework, and that's basically the idea of two-tier compilation. So underlying hidden virtual machines that are deeply coupled into the programming language or programming environment that we use, if we happen to be programming with a language with frameworks such as .NET or maybe even Java.